Have you ever wondered how engineers precisely quantify a robot's ability to move and perform tasks in its environment? Or how they ensure a robotic arm can reach exactly where it needs to go without colliding with itself or its surroundings? It all comes down to understanding the fundamental concept of motion. The number of degrees of freedom for a robot manipulator is primarily determined by a foundational principle in mechanism analysis, often expressed through the modified Grubler's formula, which is sometimes referred to as the Kutzbach criterion for mechanisms. This formula calculates the minimum number of independent parameters needed to precisely define the position and orientation of every link within the robot's kinematic chain. The core idea behind this formula stems from the fact that any unconstrained rigid body in three-dimensional space has 6 degrees of freedom, specifically 3 translational motions along the x, y, and z axes, and 3 rotational motions about those same axes. Grubler's formula accounts for the total number of links in the system, including the fixed base, and the number of joints connecting those links. Each joint imposes constraints on the relative motion between the connected links, reducing the overall degrees of freedom. The formula, m equals 6 multiplied by the quantity of n minus 1 minus j, plus the sum of f sub I, where m is the total degrees of freedom, n is the total number of links including the base, j is the total number of joints, and f sub I is the degrees of freedom allowed by each individual joint, aggregates these factors to provide the net movable degrees of freedom. To apply this effectively, you first identify all the links in the robot, remembering to count the stationary base as a link. Next, identify all the joints and determine the specific type of motion each joint permits. A revolute joint, which allows rotation about a single axis, provides 1 degree of freedom, just like a prismatic joint which allows translation along a single axis. More complex joints like spherical joints can provide 3 degrees of freedom. Once these components are identified, you simply substitute the values into the formula to calculate the manipulator's total degrees of freedom. This analytical approach helps engineers in crucial design stages, revealing if a manipulator is under-constrained, meaning it has redundant or uncontrollable movements, or over-constrained, which indicates it cannot move as intended due to excessive restrictions. For example, a robot designed with 6 revolute joints in series, where each joint axis is independent, would typically yield 6 degrees of freedom, enabling it to reach any position and orientation within its workspace. This is often seen in general-purpose industrial manipulators. Understanding and correctly applying Grubler's formula provides roboticists with a powerful tool for analyzing a robot's kinematic structure, ensuring it has the optimal number of independent movements required for its intended tasks. This precise quantification allows for the efficient design of manipulators that are neither overly complex nor insufficiently versatile, leading to robust and functional robotic systems capable of performing diverse and intricate operations.
If you love robotics, like, subscribe, and keep building with us.